Second module starts with the design of transformers. We all know transformers are classified into three. So first is depending upon the type of supply, second one is depending upon the type of construction, and third one is depending upon the service. So depending upon the type of supply, it is classified as single phase and three phase. Depending upon the type of construction, transformer is classified as core type and shell type, and depending upon the service, it is classified as power transformer and distribution transformer. So we all know about this classification. We had already studied or learned from our lower semester itself. So what is transformer? It's a static device used to transfer voltage from one level to another level with a constant power. So let's see single phase core type transformer. This is the diagram of single phase core type transformer. So for single phase core type transformer, there is only one window. Okay, this is the window. This is the limbs or leg, and outer portion is the yoke. And this is the primary winding section, and this is the secondary winding section. Moving on to the single phase shell type transformer. So these are the windings, and this is the yoke, and this is the side limb, and this is the center limb. Moving on to the three phase core type transformer. So for the three phase core type transformer, there are two windows. One is this and one is this. There are two windows for three phase core type transformers. So you all have to know this clearly. For single phase transformer, there is only one window, and for three phase transformer, there are two windows. And this is the primary winding section, and these are the secondary winding sections. Okay, so this is the bottom yoke, and this is the leg, and this is the top yoke. So moving on to the three phase shell type transformer. This is three phase shell type transformer. These are the primary three phase windings, and these are the secondary three phase windings. So moving on to the distribution transformers and power transformer differences. So what's the difference between distribution transformers and power transformers? Normally distribution transformer is just up to 500 kVA. Okay, and power transfer is we can use above 500 kVA. And also distributed transformer is designed for good all day efficiency, and it has good voltage regulation, whereas in the case of power transformers, it is normally used where in substations and generating stations, and also it is designed to have maximum efficiency. So let's go to the output of transformer, or let's go to the design details of transformers. So we need to study basically the single phase output equation of transformers and three phase output equations of transformers. Before going in detail with the derivation, let's familiarize with the notations. So moving on to design details, output of transformers, let phi m is the main flux in Web. Bm is the maximum flux density, that is in Weber per meter square. We need to know all the units. Delta is the current density, ampere per meter square. AGI is the gross core area in meter square. AI is the net gross area in meter square. And capital AI is equal to stacking factor into gross core area. And capital AC is the area of copper in the window in meter square. And AW is the window area in meter square. Capital D is the distance between core centers in meter. Small d is the diameter of circumscribing circle, that is in meter. Kw is the window space factor. F, as you all know, it is the frequency in hertz. Capital E suffix T is the EMF per turn in volt. So ET is the EMF per turn in volt. TP, TS are the number of turns in primary and secondary respectively. IP and IS are the current in primary and secondary respectively, that is in ampere. VP and VS are the terminal voltages of primary and secondary windings respectively in volt. And AP and AS are the area of conductors of primary and secondary respectively. So let's familiarize the core type and shell type. So this is the AW. So that is the what? Area of window. Okay, so window area is AW and capital D. So as all you can see, capital D here to here. Capital D is the distance between core centers in meter, and small d is the distance, diameter, diameter of circumscribing circle. And for the shell type, this is AW. AW is the window area and small d is the distance of circumscribing circle, and capital D is the distance between core centers in meter. You have to learn this figure also and also the notations clearly. Moving on to the derivations. First is single phase transformer. So first we need to know the voltage per turn equation or the EMF induced in a transformer. That is E suffix T is equal to 4.44 phi m F. That is equal to what? Voltage per turn. That is E by capital T, equation number 1. So induced EMF in a transformer is ET is equal to 4.44 phi m F. That is also equal to voltage per turn. So it is given as capital E by T. So next we need to find the total copper area in window. So for single phase transformer, it contains one primary and one secondary winding. Therefore, total area of copper in window is equal to copper area of primary window plus copper area of secondary window. So copper area of primary window means primary turns into area of primary conductor plus secondary turns into area of secondary conductor. So AC is equal to primary turns into area of primary conductor, that is TP AP plus TS AS. For single phase transformer, AC is equal to TP AP plus TS AS. Whereas in the case of three phase transformer, the window is 2. Therefore, what happened? Area of copper area in window is equal to 2 into the whole equation. This equation will change into A is equal to 2 into the whole equation in the case of three phase transformer. That is the basic difference in the derivation between single phase and three phase. Okay, so continue with the derivations. First we need to know the induced EMF in a transformer, then total area of copper in a window. Okay, that we got as AC is equal to TPAP plus TSAS. So we all know that area is equal to normally current divided by density, isn't it? So like that, AP, area in the primary section, that is equal to IP by delta. Similarly, area in the secondary winding is equal to IS by delta. So when we substitute these both in this equation, total area of copper is equal to TP IP plus TS IS by delta, where TP into IP, what is turns into current, is always ampere turn, right? That is equal to MMF. So if we neglect magnetizing current, all TP by IP is equal to TS by IS equal to AT. Therefore, AC is equal to 2AT by delta. Okay, understood? By neglecting magnetizing current, these terms TP, IP plus equal to TS, IS is equal to ampere turn. Therefore, AC is equal to 2AT by delta. So next we need to find window space factor KW, that is equal to conductor area in window by total area of window, that is equal to AC by AW. From here we will get the value of AC as KW into AW. So substitute this AC in equation number 2. Okay, so we will get the equation as AT is equal to ampere turn is equal to AW KW delta by 2. Now next we need to know the rating of single phase transformer in kVA. Okay, the rating of single phase transformer in kVA is given as what? Q is equal to Vp Ip into 10 raised to minus 3 kVA. So you don't need to change it into kVA. It is already changed it into kVA as 10 raised to minus 3 kVA. Okay, so you need to be careful here. So Q is equal to Vp Ip into 10 raised to minus 3 kVA. So this Vp Ip can be replaced as Ep Ip into 10 raised to minus 3. Now, this EP we can write as EP is equal to ET into TP. So, in the first equation is already given. See, this ET, induced EMF in transformer, ET is equal to capital E by T. From here, we got this equation as EP is equal to ET into TP. So, we are substituting this in here. So, we will get as ET dot TP into IP into 10 raised to minus 3. Okay. Now, this TP into IP, that is turns into current, is always is ampere turn. So, ET AT into 10 raised to minus 3. Okay. Putting this equation in putting equation number 5, that is this equation here, we will get equation as Q is equal to ET into AW KW delta by 2 into 10 raised to minus 3. Also, we know that ET is equal, induced EMF is equal 4.44 phi mF. So, we are replacing this into here. Okay, so we will get the equation of Q is equal to 4.44 phi mF into AW KW by 2 delta and 10 raised to minus 3. So, dividing this by this, so we will get as Q is equal to 2.22 phi mF into AW KW delta and 10 raised to minus 3. Also, we can replace the phi m as Bm into AI. Therefore, the final equation, output equation of a transformer for single phase transformer is Q is equal to what? 2.22 BMF AI AW KW delta into 10 raised to minus 3 kWA. We need to study this by heart in order to solve the transformer equation. Therefore, Q is equal to what? 2.22 F BM AI AW KW delta into 10 raised to minus 3 kVA. So, this is a single phase transformer output equation. If you know the single phase transformer equation, it is easy to derive three phase transformer equation. As I said earlier, the only change is we need to change here. AC is equal to what? For the three phase transformer, there will be two windows. So, the equation will become AC equal to 2 into TPAP plus TSAS. See? All of the changes happened here. Then we are again going with the AC. Okay, we will get as ampere turn like this. Then again here also there is a change. For three phase transformer, the equation is 3 into VPIP in 10 raised to minus 3 kV. Whereas for a single phase transformer, what was the equation? See, for a single phase transformer, the rating in kV is given as Q is your VPIP in 10 raised to minus 3 kV. For 3 phase, it is equal to 3 VPIP into 10 raised to minus 3 kVA. So, we will get the final equation as Q is equal to 3.33. Okay, it's easy for you to remember because for single phase it was 2.22 and for 3 phase it changed into, after multiplication calculation, it is changed into 3.33. Rest is same only. F BM KW AWAI delta into 10 raised to minus 3 kVA. Okay, so these two are the equations for single phase and three phase transformer.